Hello and welcome to the opening ceremony of the Carl Zeiss Foundation 3D Manufacturing User Lab. My name is Gernot Goll and I'm head of the NSL, the Nanostructure Service Laboratory at KIT. We organize the Carl Zeiss Foundation 3D User Lab. We are here in the basement of the CFN building, one floor below you, our guests in the lobby of the CFN building. As you may notice, I changed my clothing, and also the equipment of the video crew has been cleaned. The reason is that we are entering a clean room lab now. A clean room lab is a special environment where the particulate air cleanliness is lowered by several orders of magnitude, compared of course to the environmental conditions. This is necessary because a contamination with particles from air would lead to a failure of the structures we create here by lithography. So a typical size of our structures is between several microns down to a few tenths of nanometers. Just as a note for the experts, this clean room here is classified according to international standard as ISO 6 and ISO 7 clean room labs. Let us now enter the clean room. So now we are inside, and on the left and right side of this corridor we have different labs. Labs for e-beam lithography, labs for focused ion beam, structuring, optical lithography, and also labs for processing, post-processing, like dry etching and evaporation tools. You may wonder about the fancy illumination here. The reason is that most resists are sensitive in the blue and UV range. And this means we have to avoid exposure by the light from the ceiling. And therefore we work in some kind of dark room with yellow light instead of red light. Now follow me to the 3D manufacturing lab of the Carl Zeiss Foundation. So now we are inside the new Carl Zeiss Foundation 3D Manufacturing User Lab. First plans to erect this lab went back to 2018. With the confirmation of the support by the Carl Zeiss Foundation within the Cluster of Excellence 3D Matter Made to Order, we could further develop these plans. In April 2020, during the COVID pandemic, the first walls have been erected here in this lab. And already in November of the same year, the first device was delivered and went into operation. Finally, in December last year, we got the certificate for ISO 7 clean room. At the moment, 20 of 120 registered users of the Nanostructure Service Lab are members of the cluster 3D Matter Made to Order. And they exclusively use this Carl Zeiss Foundation 3D User Lab. Several devices are available here. I hand over now to Sebastian Kalt, Pascal Kiefer, and Dr. Silvia Diewald, who will give a short explanation of the devices.
Hello, my name is Sebastian Kalt. I'm a doctoral researcher in a group of Martin Wegener and also a member of the Class of Excellence 3D M2O. I'm also a device manager of the Nanoscribe Photonics Professional GT, or PPGT in short. It's a state-of-the-art optical 3D printer that can be used to fabricate 3D and 2D structures in the micro and mesoscale with surface and feature sizes in the sub-micron range. The PPGT, as it can be seen here, uses a 3D printing technique that is called direct laser writing or 3D laser nanoprinting. In 3D laser nanoprinting, we use a femtosecond pulse laser, which is tightly focused into a liquid photoresist. A photoresist usually consists of different components, but the most important ones are a monomer and a photoinitiator. In the focus region, the intensities are large enough to trigger this polymerization reaction. This is really important because only in the focal region this intensity is large enough to start this polymerization or cross-linking reaction. If we now scan our laser focus through the liquid photoresist along arbitrary trajectories, we can basically 3D print every type of 2D or 3D structure that we want. This is really important because now we can just add up these focus points, which we also call volumetric pixels or voxels, to add up to a 3D structure. This allows us for obviously many cool applications, and for example, one thing that we did in the past is the 3D printing of optical microcomponents. You can also print, for example, cell scaffolds for biological applications, which mean that you have to print multi-material, functionalized materials so that you can study the behavior of cells, for example, under the influence of an external stimulus. What we also did is the printing on optical fiber tips, on electronic chips, for example, but also on conventional substrates like glass substrates or silicon wafers, for example. As I said, this allows us to fabricate multiple structures with specially tailored functions. For example, you can also think of printing inside of synthetic cells or other biological applications. So in summary, the PPGT is a highly functional, super sophisticated system that can be used in many applications, not only, but mainly in the fields of physics, biology, chemistry, but also in electrical, mechanical engineering, as well as material science. But however, in some cases you need really good surface quality, and for this you would not use this technique, but a different 3D printing technique, which is called two-photon grayscale lithography. And with this I would like to hand over to Pascal Kiefer, who will give us a quick introduction into this technique.
Hello, I'm Pascal Kiefer, and I'm also a doctoral researcher in the Cluster of Excellence and in the group of Martin Wegener. I'm the device manager of the Nanoscribe Quantum X, which is part of the newest product series of Nanoscribe. While the PPGT is very flexible in a broad range of applications, Quantum X has been specifically optimized for the fabrication of micro-optical components. This includes, for example, diffractive optical elements or micro-lens arrays. While for the previous device, the voxel size you 3D print your sample is fixed. For the Quantum X, however, the voxel size is adjusted continuously while printing to fix your target structure. On the one hand, this saves you a lot of printing time, since for bulky regions of your structure, you can simply use very large voxel sizes. On the other hand, you also gain a lot of precision, because you can use very small voxel sizes for very sharp edges or regions of your structure. Furthermore, the control of this voxel size is very high, since Quantum X features an advanced control of the laser power in comparison to the Photonic Professional GT. All of this together enables to 3D print samples with a surface roughness of only a few nanometers, which is especially advantageous for the production of micro-optical components like micro-lens arrays. For lenses, you want smooth surfaces. In principle, you can print any and full 3D structures like for the PPGT. To do this, you just take a 3D file, for example in the STL format, and you process this with the QuantumX software. Afterwards, after you have created such a corresponding job file for the machine, you simply take a glass or silicon substrate, as well as the objective lens, which is suitable for the photoresist you use, together with the photoresist, and you insert this into the machine. Then you just put a few settings, and then you can start your print job. This is all done automatically, and you can even supervise the progress of your print job remotely. Using such 3D files has been already known for other instruments. However, to use the full capabilities of these variable voxel sizes, we use grayscale images here. For grayscale images, your structure is defined by discrete pixels with a defined brightness. And by using grayscale images, the handling of complex structures is way easier before. However, you have the boundary condition of printing 2.5D structures instead of full 3D structures. Yet this is perfectly fine with the application for micro-optical components, which are also mostly 2.5D. Furthermore, for very small structure heights, you can just simply scan through the whole print field once and just adjust the voxel size on the go. You can see this at this print job, which is running at the moment. So to summarize, the workflow for QuantumX is very simple and easy to learn, and this makes it very accessible, especially for new users. After you have then successfully continued and finished your print job, you can just take out the substrate and dissolve the remaining liquid photoresist in a development solution. Afterwards, only the solidified part remains, and you can, for example, characterize your 3D printed sample with a confocal microscope. Here, Silvia Diewald will say a few words about how that is done.
Hello, I'm Silvia Diewald, and I usually work in the NSL cleanroom next door, but today I want to show you one of those shiny new devices we have here in the CZF user lab. It's the Mars FCM Explorer in front of me, and it's a confocal microscope that we use to routinely inspect most of the 3D printed samples we fabricate here. We use it for documentation, but also for analyzing the surface roughness or to look for fabrication faults. To show you the device in action, Pascal has prepared a sample on the QuantumX with an array of diffractive optical elements. And so let's just have a look how this looks like. Start a measurement. During the measurement, the sample is moved along the z-axis in and out of focus, and the software analyzes the incoming data, stores everything that's in focus, and discards everything that's out of focus. It's actually a neat trick to get a set resolution that's better than you would just expect from the optical resolution. And in the end, all the data that's collected is used to get a 3D reconstruction of our surface. And it seems that in this case, we have a kind of a diffuser.
Okay, thank you, Silvia, Pascal, and Sebastian, for your information. If you want to get more information about the Carl Zeiss Foundation 3D User Lab, or if you want to know how to get access, please visit our webpage or contact me directly. Okay, so I thank you again for visiting the Carl Zeiss Foundation 3D Manufacturing User Lab. I will you see upstairs soon. Thank you again.